Loving Father, we thank you for the gift of life. Thank you for your protection, the love, the care, and each and everything that you have granted us. As we are commencing our lesson, we pray that you may guide us, may lead us, may send us the Holy Spirit, that you may be able to grasp each and everything that is going to be taught. May you guide our facilitator of the day, and we pray that you may fully be there with us during the whole session. Pray this through Christ our Lord.
Amen. Thank you so much, Christine, for the word of prayer, and good afternoon, everyone. In our session today, we are going to look at the area in calculus, and we are going to look at the trapezium rule. That is what we are going to be looking at in our session today. Now, what are you supposed to know at the end of the day? Our competence is that by the time you finish this session, you must be in position to estimate definite integrals and areas under curves to solve problems that involve numerical integration. That is what you need to be knowing. Now, as we approach this area of numerical integration, I want to bring to your attention that we have various ways you can obtain an area, you can attain an accumulation over time. But the major method we are going to concentrate on is going to be the trapezium rule. And by the end of this session, our learning outcome is you must be in position to evaluate a definite integral and be in position to estimate an area under the curve. As we start, I want you to know that the trapezium rule or any numerical approach we usually use is an estimate, but it does not give us an exact value. It is the analytical approaches that will always give you an exact value, but numerical approaches will always give us a value close to the exact value. Sometimes it may be the same value, sometimes it may be a bit far away from it, but always there will be an error in the estimated value. Like whenever you estimate something, that means you are not exact, but you may be close to that exact value. Take an example. Some of you, I know you have been at the source of the Nile, those who have gone to the eastern part of the country. And when you look at the area where we have our River Nile, or where you will find such, you may want to estimate the area that has been covered by the water. But when you look at it, you notice that the area has a bit of curve. The area is not like a clear shape, but you want to find out what is that area that is covering this water, where the water is covering. Now, for you to be able to estimate such an area, you can go on and develop a model and use numerical estimations to come up with the real or with the estimated area. All the area you see, more so when the area is not an exact shape, let me say it can be land, more so when the shape is not clear, then there we go on and apply what we call the numerical approaches. Even when it comes to the reservoirs, like those areas that they usually reserve on the roads, you want to estimate the area, most of the curves, most of the curve things, you will notice that for such, in order for you to estimate, you can use what we call numerical approaches. And that's what we are going to look at today. The knowledge you are going to acquire can be applied in mathematics, can be applied in biology. Those who are doing biology, sometimes you may model and you want to see how something accumulates over time. Take an example. Sometimes we eat some things and there are some bacteria that might be contained within what we are eating and the rest of that. So those things can accumulate over time. So those things that accumulate over time, you want to estimate the area of something. all those ones we shall use. Some of you are doing cryptocurrency. Those things of economics are, coin and the rest of that. Still, you can make some estimation on the cost curves, and then you come up with the amount or the area you should be able to expect at the end of the day. Now, that is the application of what you are learning. In case they want to estimate it, this is how they can estimate it in real life. They can estimate those areas, but many times now they use aerial view. They can use the aerial view to come up with those estimated areas. And this is the topic we are going to look at today. So where are we going to apply, or where can the rule we are going to look at apply? It can be in engineering, it can be in economics, the distances traveled, the accumulations of bacteria, and the rest of that. So all that can be modeled using the trapezium rule. Now, what is the trapezium rule? A trapezium rule is that approach that we use to estimate the area under a given curve. I repeat, we use it to estimate the area under a curve. So meaning that for it, we shall mainly look at those cyclical things, those cyclical things, those things that give us curves. Those are the things that we are mainly going to look at. And you will notice that the functions that will be given to you, many of those functions are going to be functions that yield curves. So let me know whether we are good now to dive into the session. That was just a brief, but now I want to dive into what we call the trapezium rule. How does it look like, and how we can derive it? We are good? Akanawa says we go. Yes. Okay. Now we are going to start. When you look at my screen, this is a curve. And you know that when I have a curve, this is my line, this is one line, and this is another line that I may have on my curve. So I'm going to have these lines here, and I will label them very well, that this is these are my lines. We know very well that this is what we call our x-axis, and you know that this is my y-axis. Take an example. You may have a curve. Let me say you have a curve maybe that goes like this. I'm going to just use an estimate of a curve. Let me say this is your curve. And you may be interested in finding the area of this curve. Let me say you are interested in finding the area of this curve, maybe the area, let me say, from this point here up to maybe this point here. And what are you interested in? You want to know what is the area covered around this area. Now, for such to be able to obtain them, you can use the numerical, the analytical approach, the one of integration and the rest of that. So let me say this curve of ours here, I'm going to call it that it is my y equals to f of x. And my fx can be any function of my choice as long as it gives me a cyclic or it gives me this kind of curve. Now, in order for me to find the area under the curve, let me say the area, let me say this starting point here is A up to where I have B. To find the area under this curve, what can I do? Now, in order for you to use the estimation approach, we use, like from the word, we can keep on accumulating the different areas and then we add them. How do we estimate? How do we get the areas? I'm going to use, I use which color? Let me use this color. I can estimate them by dividing. So here, those are 2 centimeters. Those are my 2 centimeters. Those are my 2 centimeters. And these are my 2 centimeters. You are going to allow me to add on one more such that I have 2 centimeters. Okay. But in case I stop here, it means that I'm going to you are going to allow me that I end around this point maybe. Maybe I end here. This is where my B is. Now, what do you notice? That since this is my x-axis and my starting point is here, this is what I'm going to call x. But since it is the starting point, I can call it x naught. But when I'm estimating, the second one is going to be x1. This one can be x2. This one can be x3. This one can be x4. But I want to let you know that here you can have as many as you can. So you can have very many triangles, like very many triangles as you want. Now, what are you noticing? What you are noticing here is that since I want to estimate, this is what is going to happen. Hope you are seeing, eh? Now, if that is what is going to happen on our graph, now this part here, this part here is what always brings about the error when we are using the estimation method. Because at the end of the day, I want you to pay attention that at the end of the day, what am I aiming at? I'm aiming at getting what we call the a trapezium. So when you look at it very well, I'm forming what we call the trapezium. But because we are not accurate, a real trapezium, because from the start, maybe would have been something like this. So you are not so accurate. So that's why we always accumulate what we call an error. Yes, and here, because I'm a bit more accurate, you'll notice that if when you draw a line from one point to another, from x0 to x1, it does not, you'll find that your curve, in case this is the curve, there is an area here that has not been catered for. Now, along the y, this point here, since this is the y-axis, this point here corresponds to your y naught. This second point here is the one that corresponds to your y1. The next point here will correspond to y2. The next point here corresponds to y3. The next point here will correspond to your y4. The y value, the way you get them in your curves. Now, when we are using trapezium rule, I want you to notice that the figure I'm forming inside here, when you look at it very well, you are noticing that the figure is a trapezium. This figure here looks like a trapezium. When you look at the first one, also it looks like a trapezium. And that's where we derive the name trapezium rule. So in order for us to estimate the area under this curve, it means that I'm going to add the area of the first trapezium. I get the area of the second, the area of the third trapezium, the area of the fourth trapezium. I add up all those trapeziums that I have within my curve. And the area under it is what will give us what we call our value. And in the analytical approach, that is what we call integration. So integration means that sum up all those small areas. At the end, what you get, the total area, is what we call the integration thing of it. Now, that is how we are going to be estimating what we call the area under a curve. So before I start, in case you have a question, ask, because now we have started.
Good
Ask,
afternoon, teacher.
Deborah. Yes.
Teacher, I've gotten a problem with my network, so I literally missed out from the very beginning of you inserting the trapeziums on the graph. Can you
Okay,
please
okay.
make a review?
Yes, we are going to.
Thank you, teacher.
Okay. Okay, now members, that is how you do it on the graphical approach. So you'll notice that the moment you draw your curve here, you'll always find that, let me say I've drawn my curve like this. So when you estimate, but I want you always to know that between any two of them, that you must have equal space here. The space must be equal. So when you try to draw your trapeziums here, you will notice that there is always an error, or there is always space that you have not been able to cater for. So that space that you are not able to cater for is what brings about the error in estimation approaches. So now allow me to use now a permanent marker. allow me to use a permanent one, and then we start. Now, members, if this is my axis and this is my y-axis, so I'm going to have this as my y and I'll have this as my x. And this is the curve. I'm going to use that curve. So inside the curve, like we have said, we are going to have different trapeziums. So allow me to get the different trapezium. That is the second. But the space in between should always be the same. Now, what are we going to do? Like I've said, the x naught, this is the starting point. I'll have x1, I'll have x2, I'll have x3, I'll have up to. Here, you remember, you can go on up to the. So I'm going to add on more here to make it match. So this one can be, remember here, you can have very many in between here. You can have very many figures. So this one is going to be xn minus 1, and then the last one will be xn. So here I'm telling you that in between here, you can have very many things. Now, your x value, the x value, these values that correspond on the x-axis, this value here, this value here, this value here. Members, I want to let you know that that is what we call an ordinate. Hope that is okay. I've started now. The x values, we call them ordinates. So when you hear the word ordinates, ordinate corresponds to the x value. That is the meaning. So then, like I've said, that along the y, here, along the y, this height here is what corresponds to y here, not. The second height here corresponds to y1. The next one here corresponds to y3. So you're going to allow me, instead of writing them like that, I'm going to write that here I have y0. Here I'll have y1. Here I'll have y2. Here I'll have y3. And so on and so forth. So here, the next one here is going to be yn minus 1 and then yn. Now, after obtaining that, I want to bring to your attention, I've said x are what we call the ordinates. Now, in between here, are you noticing here? You are forming a trapezium. The trapezium. So I'm going to extract the trapezium. So you are forming something like this. You have this, you have this, you have this. This is where you have your x naught. This is where you have your x1. But like I've said, your trapezium will look like that. Now, in between here, so here up is where you have y naught. This is where you have y1. Now, in between here is what forms like the height of our trapezium. So that one, we are going to call it h. In between there, we are going to call it our h. Here, in between, like the height of the trapezium. Like the way you have, I know, sometimes you are used to this kind of what? Trapezium. So like this is your y1, this is your y0, and this is like the trapezium. Now, to get this h is what we are going to look at. Hope we okay. When you look at the second one is like having this. I have this, I have this. This is x1, and here I have my trapezium. This is x2, but this is y2, and this is y1. When you go to the next one, still the same thing is going to happen. That what do you have here? This is like y2 and this is y3. And what do you have here? This is x2 and this is x3. But like we say that the interval between any two should always be the same. So since we have said that here is we are going to call it h, also this is going to be h, also this is going to be h. Now, when I continue up to the last one here, we are going still to have the same. I'll have this, I'll have this, I'll have this. So this is going to be xn minus 1 up to xn. And then this is going to be yn minus 1, and this is going to be yn, and still my height is going to be h. Kindly let me know through the chat whether we are still on the same page. Let me know whether we are still on the same page. Okay, okay. So, are we on the same page? Oh, yes. Yes. Now, Martina, uh, the trapezium rule is the can I say is the estimation method. Now, in integration, I want you to learn that not all integrals can be integrated. There are integrals you are going to find that you cannot even integrate, whatever approach you can use when you cannot integrate. Now, for such, that's where we bring in these numerical approaches. Now, the numerical approaches are also other forms of integrating, but for them, they usually come out when things are tough, you cannot integrate it. But now at your level, we are going to look at those ones that you can integrate, and we want to show you that you can use this approach and you come up with the same answer. But like I've said, that when it comes to numerical estimations, your answer will not be exact, but it will be just an approximation to the exact value. Okay, people are saying we are on the same page. Now, if you remember very well from your knowledge of I think P7, in case this is height and this is A and this is B, you remember that to get the area of the trapezium, what was your area? Put it in the chat. What was your area of the trapezium? How were you getting it in those classes at lower level? No, it is okay, Angela. You can put the arrows. Place it in the chat if you remember. A half BH. Okay. That is a call. A half H into A plus B. A half H. Okay, good. So you remember our area was a half H into A plus B. Members, it is the same thing we are going to do. So in order to be able to get the area for the first one here, this is what I'm going to call the first trapezium, area 1. This I'm going to call it area 2. This is area 3, and this is area N. So for the first one here, our area from your trapezium here, you have said is equal to a half H. Now here, instead of A and B, we have Y0 and Y1. So we shall have Y0 plus Y1. For the second one, I will say A2 is equal to a half H Y1 plus Y2. The next one here, I'll have F3 is equal to a half H. Instead, I'll have Y2 plus Y3. And then the last one here, I'll say that my area N is equal to is going to be equal to a half H Y N minus 1 plus Yn. So that's how you get the area of the trapezium. So to get the total area under the whole of this curve here, you add up all the areas. Area 1, area 2, area 3, up to the last one. That's how we get the total area under the curve. But now, can we simplify it further? Now, to get here, I'm going to write here that to get the total area under the curve, we are going to add area 1 plus area 2 plus area 3. In case you have other areas, still you do the same, plus up to area that is the last one, which is area N. Now, when you look at the first area we got was a half H into Y0 plus Y1. When you look at the second area we got was a half H into Y1 plus Y2. Plus, when you look at the next area we got was a half H into Y2 plus Y3. Then we can add on other areas in between. Then we say plus the last one, which is a half H into yn minus 1 plus y of n. So members, when you look at all our areas in the chart, kindly let us know what is common. What is it that you see that appears almost everywhere? What is common? What is common across everything? Chris is saying a half h. Jess says saying a half h, a half h, a half h. Very good. So you notice that a half h is cutting across. When you look in the first one, you see a half h. When you look at the second one, you see a half h. So you see a half h is here, a half h is here, a half h is here, a half h is there. Meaning that a half h is a common factor. So I'm going to pull it out and say a half h. So when I pull it, the first part I remain with y0 plus y1. Then the second area I remain with y1 plus y2. When I put, I remain with y2 plus y3 plus up to the last one, which is going to be n minus 1 plus y of n. Now, what are you going to notice? That you have y0 is not repeating itself. You notice that yn is also not going to repeat. But what is going to repeat? Y1 is here, y1 is here. Y2 is here, y2 is here. Y3, y3, y4 like that. So those ones are going to repeat themselves. So meaning that now you are going to have a half of h. Y0 is not repeating. Y1 plus y2 is 2y1 plus y2 plus y2 is 2y, 2y2 plus, so the rest are going to be repeating. Y3 will repeat itself, y4 will repeat itself, plus 2 yn minus 1 plus y of n. Now, what is going to happen at the end of that day? You notice that y0 and yn is not repeating. So that is why I can write now a half h, that y0 is not repeating, and yn, but the rest are repeating. And all of them have a 2 on them, 2y1, 2y2, 2y3, like that. So I'm going to write it as 2 into y1 plus y2 plus up to yn minus 1. Kindly let me know. Are we still there? Are we still on the same page? Okay, Quantum says yes. Akana now says yes. Yes, call as people. Oh, I failed to get call bless.
Yes, teacher, good afternoon.
Good afternoon.
Yes, I wish, pardon me, from there where half height has been identified as the common factor. So downwards, this third step where I'm seeing some values repeating, how have you dealt with them?
Come again, how?
How have you dealt with these values which are common?
Common?
Like y1 plus y2, y2.
Yeah, like I'm adding, collecting like terms. y1 plus y1 is 2y1. y2 plus y2 is 2y2.
Okay, I've got it. Thank you.
Okay. So members, now what are we going to remain with? So we are going to remain with something like this. A half h into y0 plus yn plus 2 into y1 plus y2 plus up to the last one, which is n minus 1. Now, what you are seeing here, members, is what we call the trapezium rule. This is what we call the trapezium rule. Now, our graph we have here, this graph I've showed you. If this is our graph, let me name it that this is the graph y is equal to f of x. The total area under this curve is equal to this thing I have derived for you. So this is what we call the area under the curve using the estimation method. Now, using the integration part, someone was asking, what is the upper limit? We talked about upper limit and lower limit. Now, the upper limit is this last value, the one you end with here. The value, let me say this is like the upper limit, and where you start from is the lower limit. But one thing I want to bring to your attention, that whenever we are dealing with the numerical integration estimations, we always deal with values continuity, or like continuous what? Continuous values. Number two, we always divide into different trapeziums. And I want now to bring it to your attention that are you seeing this first area one is what we are going to be referring to as a sub-interval. The second one here, we shall call it the second interval. So these ones, like these ones, the area one, this is sub-interval 1, sub-interval 2, sub-interval 3, sub-interval what? 4. The different trapeziums that you are able to get are what we call the sub-intervals. If you don't want to call them sub-intervals, you can call them strips. Sometimes you can use strips, sometimes you can use what you call sub-intervals. But the values, the x value here, 1, 2, 3, 4, 5, those are what we call the ordinates. Now, can I conclude? Now, in case I'm to conclude, I will say that now my integral from a to b of that function that I have, let me say now we have called our graph y with respect to the x is always given by half h. Then I'll have here y naught plus yn, then plus 2 into y1 plus y2 plus yn minus 1, and then everything. Now this is what we call the trapezium rule. I'm going to give you an example. I'm going to give you, because now I have brought in one, I've brought in what we call the ordinates. I've also talked about what we call sub-intervals. So members, if I have, let me say this is my curve, and I have 1, 2, 3, and this is, let me say, 4. So this is my x, let me say this is 0, this is 0 0.2, this is 0 0.3, and this is 0 0.4. Members in the chat, remember we said that x values are what we call our, we say that x values are what we call ordinates. Members, you count for me. In the chat, you place how many ordinates do we have for this diagram I've drawn? How many ordinates do we have there? How many are you seeing? Jesse says 4. Very good. You are seeing 4 x values. So here it means that the number of ordinates are equal to 4. In the chart, how many trapeziums? How many trapeziums are you seeing? You put in the chat. How many trapeziums are you seeing that we have drawn? Very good. People are saying 4. Who's saying 4? Okay. People are saying 3. Because when you look at it, this is my first trapezium. Here, this is 1. This is the second, and this is the third. And I've told that those trapeziums are what we call the sub-intervals. And therefore, for this case, I will say I'll have 3 sub-intervals. Or you can call them strips, any of those two. I'm drawing another one. If I have this, T. Members, you tell me in the chat, how many ordinates are we having? How many ordinates do we have there? Members are saying we have 6 ordinates. Perfect. Members, how many sub-intervals do we have? Ordinates, we are getting 6. Very good. What about sub-intervals? You are getting 5. Perfect. That is very okay. Now, that is what we call. So, ordinates are 6. Sub-intervals are 5. Members, are you noticing that the ordinates and sub-intervals, they have a way they are related? Who has realized that? What are you noticing about ordinates? That if ordinate, the first one, ordinates were 6, sub-intervals were 5. When you looked at the second diagram, the first one, I think we had I don't remember. We had 4 and the sub-intervals are 3. So someone has said they are less by 1. They are less by 1. That is a difference of 1. So ordinates are always greater by 1. Very good. Yes, the ordinates are n sub-intervals n minus 1. Okay, very good, very good, very good. Now, in the question, they can give you a scenario when they have even drawn for you and they want you now to be able to use it to obtain. So you need to know. That's why it is always very important. Understand the meaning of those words. Because even the scenario can tell you that it was divided into four, into 4 trapeziums. 4 trapeziums were obtained. That maybe they can tell you that Martina went on to survey land and he divided the land into three trapeziums. Now, if for you did not understand what trapeziums here represent, it means that you will not be able to get what they were meaning. So that is why it is important to understand. So trapeziums, strips are what we call, yes. And therefore, depending on how you interpret, you'll always know that sub-intervals are less than 1. Ordinates are 1. And now always you look. And now when it comes to numerical estimations, the more you divide here, the more you improve on your levels of accuracy. Let me now show you. If this is our curve here, let me say this is our curve. And for me, I draw like this. I put only 2 like that. What will it mean? It means that when I bring my ruler here to estimate, I'll come like this. That this is going to be my thing. This is going to be my trapezium. You are not seeing something that here, this space, look at that space. This space that is not covered here is going to bring errors, this space here. But the moment, members, the moment you go on and increase the way you are dividing here, let me say I go on and I put more, 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 I put more like that. What will happen is that if, let me see, when I remove this, what will happen that if I go to draw my lines, I will draw a line like, let me use another color such that it is visible. So it will be like this. It will be like this. I don't know whether members are not seeing it. It will be like this. It will be like this. It will be like this. So you will notice that your trapezium is almost on the curve. So it means that the errors are going to be reduced. So the more you put the intervals, the more you put those trapeziums, or the more you increase the number of sub-intervals, the more your accuracy is. Or the more ordinates you add, the more accuracy you attain. So that is the trapezium rule. Okay. Babe, even here we can bring it in the business sense. Like I've told you that when we go to the area, those people are going to be doing any things concerning valuation of land and the rest of that. I'm going to bring that picture. I'm going to look for it. But you have seen that people, they cut plots, like plots. Now, if you want to gain more, you need to partition them very well. And the mathematical figures you use also matter. So those people who have discovered that if you want to get more plots in land, there is a given mathematical figure you have to use. And you know that that one will not waste a lot of your time. But I want to also bring to your attention that in order for you, like I know you notice that when we are getting our height, this was x1 and this was x2. So to be able to obtain the height here, you know that h will always be given by x2 minus x1. You get this value minus this value. Then divide by how many things are in between. So I'm going to call on you now to summarize in your own. So get something to write from me. I'm going to give you 3 minutes. 3 minutes. Just write anything you want from this slide. Anything that you feel will make sense to you. Anything you feel you need. So I've given you 3 minutes. I know you can take a screenshot, but I've asked you now to just, let me even add something here. Let me put here a magnitude always. I'm going to put here a magnitude. So just write in your own words what you want from this slide. Yeah. But in case you have a question, feel free to ask. The more ordinates, the more accuracy. So in case your question is using ordinates, it means that when you are commenting on how to increase the accuracy, you say the more ordinates to, yeah. Yes, Emerson. I've said, right, I've not told you to take a screenshot. It is okay to take your screenshot, but I want you to summarize in your own words what you have understood. You can copy something from here or you can pick something from here. But I want you to use the explanation you have had to, yeah. Yes, Emerson.
Good afternoon.
Yes.
I just want to confirm the difference between ordinates and sub-intervals. Ordinates, I see normally they write with
Come
the
again.
capital.
What is the question?
I just want to know the difference between sub-intervals and ordinates.
Okay. Have you been on the call or
Because
you have just joined?
I've been on the call because here small letter n represents sub-intervals. How about capital N?
Okay. So, I want someone who is going to respond to Emerson. The difference between ordinates and sub-intervals. Josephine, come. Oh, I've failed to get Josephine. Martina?
Okay, good afternoon, everyone. So basically, how me I understand it is by breaking down the word ordinate. So basically, an ordinate is like a point because, like when we are plotting, we say coordinates. So we're looking for 2 points. So an ordinate is a point. That's why teacher began by saying the ordinates are the x values. For example, now, if you look at the graph here, x1 is an ordinate. Then a sub-interval or a strip, like you just look at it like a strip. Let's say they give you a piece of cake and they tell you to cut a strip. Like you cut, I don't know, like some, longitudinal piece, like rectangular piece. Yeah. So that's how one can differentiate them.
Okay, thank you. Jimmy, you want to add something?
Master, she has said all that. That's what I also had.
Okay.
Then there is a
Angel?
question. I have a question.
Yes?
Master, here they are indicating that they are saying that percentage error is equal to exact minus approximated value over exact value times 100%. Do we include that percent sign?
It does not matter. You may or you may not.
Yeah, okay. Thank you.
Okay. Yes, but that one is just to show you that your answer you'll get, you'll have to put a percentage. Okay. I think I've given you time to write. Let us now start.
Excuse me, sir.
Yes.
I'm having a question about how we come out with that trapezium rule.
Yes, ask. Oh, I failed to get you. Okay. Now, the rest I'll be responding. Now, the area we are dealing with is an area in calculus. What does it mean? Now, when you are learning math, there are topics that are going to be connected, that you are going to use knowledge from the other topic, and you'll find it here. I want to let you know that in order for you to pass these numbers very well or to be able to do it, there are some topics you must know. Now, when we talk about calculus, it means that some of the things you need to know, one, you need to know partial fractions. I want to let you know that as we are continuing here, you may find a number that will involve using partial fractions, more so when you are when you are getting the percentage error. Two, you are going to find out that you are going to need the knowledge of your integration 1 and integration 2. 3, you are going to use the knowledge of errors. I know you have done error, those iterative methods. So you are going to find your need errors. You are going to find yourself needing knowledge of iterative things and the rest of that. Differentiation 1 and 2 are going to be part of this. So meaning that these things of calculus, they have a lot of application when it comes to rates of change, when it comes to things that accumulate. Anything that accumulates, it means that you can integrate it using your knowledge of 1 and 2. Anything that requires optimization of resources, just know that is a lot of applications. So the applications we are going to be talking about and the knowledge we are going to need, we are going to bring back all these topics as we did with this part of trapezium rule. Because now I'm going to take an assumption that you have already looked at partial fractions. I'm going to take an assumption that you have already looked at integration 1 and 2. I'm going to take an assumption you have looked at differentiation 1 and 2. So you are going to be applying the knowledge from that calculus. Okay, we are going to start with this. They have told us that using trapezium rule with 5 sub-intervals to estimate the area under the curve. Allow me to stop sharing a bit. Okay, I've stopped sharing. Yes, and I wanted to show you how this curve looks like. So when you look at that curve, I'm going to draw it here such that now you have a feel how that curve looks like. Are you seeing the curve? That is how that curve looks like. And when you look at it, they have told us to estimate, I think it is between 0 and 1. In other words, what do they want? Like I've said that when we are estimating the area, because this is a numerical thing, they want us to estimate from this point here. You are noticing from 0 to where we have 1. That is where they want us to estimate. So when you look at it very well, you notice that here you are going to divide. Let me first remove this. It means that here they want us to divide. Here, they have told us 5. So meaning you are going to say 1, 2, 3, 4. As long as the trapeziums are 5. 1, 2, 3, 4, 5. So that's how we are going to divide them. So what does it mean? It means that in order for us to know here, now since here I can easily divide according to the graph, I can easily divide. But in order for you to get this, how the size of the height of your trapezium, that's why we are going to say that to get the size, which is h, we shall say b minus a divided by n, whereby n stands for the number of sub-intervals. How many times do they want, how many trapeziums do they want you to get? That we have from 0 to 1. So that means your b is the upper limit. Your b is the upper limit and a is the lower limit. So for this curve, it will represent our domain, that we are starting from 0 up to 1. So your b is going to be 1 minus 0 divided by n, which is equal to, which is 5. So you end up with 1 out of 5. Why am I doing this? Next time, they may not give you the interval. They may not give you your n that they need to be 5. But you may need now to use your knowledge that if this is my graph and I want to have equal parts, what should I do? That between 0 and 1, I have how many boxes? That I have 5 what? Boxes. That means that if I'm to divide it into equal parts, it means that I'll get my upper value minus the lower value divided by the number of boxes I have in between, such that I get something that is equal. Let me hope members you are getting that. Remember your curriculum, they may not even give you the number of sub-intervals, but you may need to come up with them. Let me hope that is very clear. And when you want to come up with a sketch, you need to know how your sketch can look like. Are we good to go? Kindly let me know through the chat. I wanted to just show you the curve. That the things you are going to be dealing with, you'll notice that they are curves, and we are estimating the areas under the curves. Okay, some people are saying repeat a bit. What I'm saying is that when you look at my sketch here, when you look at my sketch, this is how the curve looks like in real life. Let me make it bigger. Okay, let me make it bigger like this. Now, when you look at it, they want us to estimate the area under this curve between this is 0 and where we have 1. But we have said that if you are to estimate that region between 0 and where you have 1, one of the key things you need to know that you must have trapeziums inside there. But the trapeziums you come up with must have equal heights. In other words, the heights must be equal. So when you look here, numerically, you can just say, I'm going to divide here, I'm going to divide here, I'm going to divide here, I'm going to come here, and I'll come here. That is what you can do numerically. That's how you can do it. And in order for you to estimate now, let me use another color. In order for you to estimate, it means that now you'll come and you start drawing your trapeziums like this, like this, like this. You are not saying like this and like this, like that. So that is how it will look like. So that's why now when you count, you'll find that now you have, oh, what has happened? Oh, okay, sorry, it's okay. I've seen. I have moved the graph. Oh, let me move it back. So okay, yeah. So when you look at it, you notice that now, okay, you notice that now you can easily form them that this is 1, 2, 3, 4, and 5. So that's why we say that the number of subintervals show how many trapeziums you can obtain. Now, what do I want to bring to your attention? Next time, they may not give you the number of subintervals, but it might come from your head that if they have given me an area between 0 and 1, and I want to do what? To divide them into equal intervals. How can I do it? So that is why you need now to understand. Yeah. Take an example. Next time, let me say, they may not give it to you like this. And they may just say, let me say, between maybe 0 and maybe a value like maybe 1.6, like that. Then you need to know that, in between there, how many boxes can I have that this one can be 1, 2, 3, 4, 5, 6. As long as the in between here is the same. That's what matters a lot. That's why it is very key. Understand. Because next time even there may be graphs. You may find yourself that you have a graph they have given you, or they have told you to draw a graph, and you are supposed to estimate yourself. How do we sketch the curve? Yes, like the curve here it comes from the question. Like remember the question they have given us 1 out of 1 plus x squared. Now this is what you sketch. So you say 1 out of 1 plus x squared. Now that's why we bring in your knowledge of curve sketching in differentiation 2. You looked at curve sketching. Now that's where that knowledge now has to apply. So in other words, they can bring for you this number, but when it requires you to draw a sketch of the graph and then estimate the area of a given interval. Yes, Jimmy. Members, are
Master,
we on the same page now?
Master, is it a master that we should always draw the curve?
No, it's not a must, but here I'm just using for understanding that a scenario can come from any angle. So you just need to be ready. And I'm showing you how different topics can be integrated together.
Another thing, Master. You had said that from 0 to 1, we should have like 5 ordinates, subordinates.
Not ordinates. Ordinates are 6.
Sub-intervals, I mean. Then, Master, I can also have 10 of them.
Yes, which is okay.
Okay.
But in case the question has specified, it is okay. In case they have not specified, then that's where you go on. That's what I wanted to bring to your attention. That sometimes they may specify, another time they may not specify.
Okay. Thank you, Master.
Okay. Okay, now we are going to continue. And I also want to ask you that when you are using some words, please be careful. Use the right words. Like those x value ordinates, those are that is the domain. That's not called a range. Range means y values, vertical values, the y values. Okay, now we are going to start on this number. Now, always when we go back to our formula we obtained, we saw that what shall we have? You notice that in your formula we had a to b the integral of y with respect to the x, and we obtain a half of h into y naught plus y n then plus 2 into y1 plus y2 plus up to yn minus 1. That was our formula. Now, what do you notice? When you look at it here, you notice that there are things you need to know from your formula. Number one is h, whereby h stands for the height. It stands for that value between here and here, like the height of the trapezium. That is what h stands for. Then y naught corresponds to the y value. This is your function. That means that your function of y is 1 out of 1 plus x squared. Now, your value of y naught corresponds to the value when you have substituted in the first ordinate. y2, yn corresponds to the value when you have put in the last ordinate. Now, I want you, these formulas, please, I will request that be knowing them in your head. Put them in your head. Let us reduce on using the logbook. Let's have them in our heads. So b minus a out of n. N stands for the number of sub-intervals. And in case it is not given for a given scenario, it is okay to estimate using any of the values. But I will always advise that you look at the like what has been given to you. Let me say 1 to 2 and estimate better. Why? It is always better to use those values that don't give you a lot of recurring decimals. It is okay to use 3. But in case now you are using 3, remember it will say 1 minus 2 out of 3. So it will be 1 out of 3. So you notice that you may end up getting a lot of what? Recurring decimals, which will affect you at the end, more so for accuracy purposes. So better to get those decimals that don't have a lot of recurring decimals. So you need to be more strategic on how many sub-intervals you pick. So now the first thing we always obtain is your h, the height of your trapezium. So it is going to be h. B stands for the upper limit. So for our case here, our b is 1 and our lower limit is 0. So we are going to have 1 minus 0 divided by n, which is 5. And therefore, we shall have our h as 1 out of 5. So that means that if you have drawn, like I've showed you how our thing looks like, here, I want you to do note here our h, 1 out of 5 is the same as 0.2. It is okay to write it in decimal point. But in case that decimal number doesn't terminate, always leave it in fraction form. In case it doesn't terminate, leave it in fraction form. Number 2, when you are starting your x naught, like the first value of x naught, it must start from here where your curve is starting. So for our case, the first value is 0. So that means you are going to start from 0. As you get the second ordinate, add on what you have as your height. So here it's going to be 0.2. Add on the second one. Remember now, you keep on accumulating. So the first one was 0. On 0, add on 0.2. So it's going to be 0.2. Keep on adding on 0.2. So here it's going to be 0.4. Add on 0.2 is going to be 0.6. Add on 0.2 is going to be 0.8. Add on 0.2 is going to be 1. In case you are using the calculator, how do you know that what you are doing is okay? The first ordinate and the last ordinate must correspond to your limit, to the lower limit and the upper limit. Number 2, the difference between any two ordinates, let me say I pick randomly any two consecutive ordinates, 0.8 and maybe 0.6, the answer I get must be corresponding to my h. So in other words, the height in between the two must always be equal. That is the first thing. And always show your working. Show the working. So we are going to go on, and now our next is to obtain y naught, yn, y1, y2, and the rest of that. Now when you look here, we shall have our y naught, y1, y2, y3, y4, and y5. So that's where your formula will end. So it is up to you depending on how you want, but sometimes people love using the table. So you are going to allow me to use the table. In the table approach, I'm going to have my table here. Now in my table, I'm going to have my x, which are my ordinates. So I'm going to have my x, and the first x is your first ordinate, which is 0. The next one, you add on your sub-intervals, like the height, which is 0.2. Add on the next one, which is 0.4. Add on the next one, which is 0.6. Add on the next one, which is 0.8. Add on the next one, which is a 1. Like that. Then the next thing we are going to have here in our table, depending on how you want it, it depends. Sometimes people want simple one, whereby they want always here to have their y naught and also their yn. The first one and the last one, which is very okay. Then this side, sometimes people love to start from their y1 up to where they have n minus 1, which is also very okay. So it depends what you want, but there is no harm also substituting here all the values at once. So it depends on what you want. But here there is no any penalty whether you have separated your y or not. So someone can just put here the y values and then he substitutes in. Then you remember your y, what we had as our y was 1 out of 1 plus x squared. So you start substituting in. Where there is x, you put 0. So you come here and say, what shall we have? Y is equal to 1 out of 1 plus 0, which is 1. So here I'll put my 1. Then I go to the next one. When I have my x is equal to 0.2, so you put in. You say y now is going to be 1 plus 0.2 squared. Then you compute very well on your calculator. In case you know how to place the calc very well, it is very okay. You can place this function in the calc and you get the answer. So I'm going to have something like this. Now here, the next one for 0.2, I'm getting 0.9615. I'm going to advise that whenever you are dealing with these ones where you have decimals, write to at least 4 decimal places. But because I want to be more accurate, I'm going to increase to 5. So it is okay. Yeah. So can we go on and get the rest of the values up to when you get 1? Like I've said, some people may prefer putting it this side. There is no harm. There is no harm. It depends on how you have been trained. There is no harm. So allow me to put it that way. But here, like when I have 0, here I'm getting 1. So you substitute in, put 0.4, put 0.6, put the answer. 0.8, put the answer. So let's do that for our table. But I've said the more number of decimal points you put, the more you are going to be accurate. Yeah. So let's compute, put in your calc. Just confirm that they correspond to what I have also here. Just make sure that they correspond to what we have here. In case they don't, yeah, then you can let me know. Maybe I'm making a mistake somewhere. Yeah. Let me know. Then the last one for 1 is going to be 0.5. Okay. Members, do we have the same? Eh. Yeah. Hey, yes, yes, yes. Members are asking, do we use approximation sign? The answer is yes. Here, make sure that you use an approximation sign because this is not an accurate value. So, always it is important, use estimation. It is very key. In case your answers are, okay, members are telling me, okay, very good, very good. Members, now when you look at our formula, why people always, or why sometimes people prefer to have them like this, it is because when you look at our formula here, the first value and the last value are added together. And the other values that come are multiplied by 2. So that's why people prefer not to add them. So can you get the add 1 plus 1 here? I think it is 1.5. Add for me what you get this side as well. I'm also going to add on my calculator and see what I end up with. So also add and see what you end up with. On my calculator, this is what I'm coming up with. So add. In case you agree with mine, something like that. That's what I'm getting as I pick on a hand. Yes, Emmanuel?
Yes, Master. Master, I'm kindly requesting to repeat for me how you got up to that table. I got poor communication.
No, the table we are. Do you know what the ordinates are?
Yes.
The table is where we are bringing our ordinates. So the table has the ordinates, which are the x values here.
Okay. Yes.
Then the y and the y naught, those are the like on your trapezium, your A and B. So this is the
Yes.
height, like not, I don't want to call it the height, but the sides, the length of the trapeziums.
Okay.
Is what we have here. Hope that is okay.
Okay. Now, why are we putting it to 5 decimal points?
Because remember, this is an estimation method, and we have not yet even obtained the answer. So that's why we need to keep it such that we improve on the levels of accuracy. But with the moment you write few decimal places, it means you are not going to be
accurate.
Yes.
Okay, Master. Thank you.
Okay. So, okay, we are going to continue. Just you can ask. So, I'm going to continue here. Yes.
My question was like, is it a math that we begin with 0 for every number, or it is according to the limit?
Perfect. The last one is true, according to the limits.
Okay, sir.
Yeah, like you saw the graph, like the way you saw the graph, they can tell you to estimate in different regions. Okay. So members, we are going to continue and say this is a half. Our h here, we got our answer 0.2. And now our y naught, we got our value was 1.5 plus 2 into, here we had 3.168657, like that. So here, approximate, so this is 1 out of 2 times 0.2 into, that time was 2 plus 1.5. Here in the everything, I'm ending up with 7.837314. And when I go on to do the mathematics times 0.2 divided by 2, I end up with an answer of 0.78371314. Yeah. Now, in case the question has told me to write to a given number of decimal places, I can write. But always better at least 4 decimal points. So this is the area under the curve. So you are going to make your conclusion because this is area and we shall say these are square units. Because it is area. So you say, depending on how they have asked, you say that the area under the curve is approximately 0.2 this square units. Okay. Now, but in case you don't want, members, please take note. It's not a must to draw the table. Someone who doesn't want may come and just substitute directly here, the values. That is also very fine. Those who are not interested in the table. So you can come and put your values directly there in the table without drawing the table. Okay. Members, are we good to continue?
Yes.
A. Why we use approximate method? We have said that this method is not an accurate method. Like I showed you, you note that there are some errors. Your trapezium doesn't have a good shape at the end. So there are some things, there are some spaces that are always lost in the process. Okay, now we are going to continue. Now, when you look at the second number, they asked us to estimate, to find the percentage error in our estimation. Now, to get our percentage error for part B, you know that to get that percentage error, one, we need to know the accurate value or the exact value. The exact value is one that you are going to obtain by numerical, by integration, analytical one. That is the meaning. So we know that percentage error, we are going to have our magnitude of our exact value minus the estimated value or the approximate value, then divide by your exact value, then times 100. That is the meaning, times 100. So that means that the first thing you are going to get is the exact value. That's why we say that knowing how to integrate is important. So, and here when they tell us to integrate, you may find that sometimes it may require using integration by parts. It may require to use integration by substitution or whatever. So that's why you need to be well conversant with integration. So here we have 1 out of 1 plus x squared with respect to the x. This is 0 and this is 1. Now, when you look at this function, those who attended the morning lesson, which kind of substitution are we going to make? Anita has said this is tan substitution. Very good. So since in our denominator we have already an x squared, then we are going to use the tan substitution. Perfect. I know some of you were not able, but here we are going to say that 1 plus tan squared theta is the same as sec squared of theta. But since we have 1 plus x squared, we shall say that now 1 plus tan squared theta, I want it to equate to 1x squared. So you notice that your 1 here and the 1 here are going to go. So we shall end up with our tan squared theta equals to x squared. So to remove the squared, take a root, take a root. Therefore, we shall have tan theta equals to x. Now we go on and differentiate. Hope you are noticing that the knowledge must be there. So when you differentiate this, you get sec squared theta with respect to the theta is equal to the x. And therefore, we can come to our integral here. Now, if you want, since here you have already obtained your x equals to tan theta, it is very okay to change the limits. But if you are not interested, you can have the limits at a later time. Anything you want, it can come on later. So allow me to bring in the limits later. So here I'm going to have an integral of 1 out of 1 plus x squared, we have said is the same as 1 plus tan squared theta times dx, which is the same as sec squared theta d theta. So what is going to happen? 1 plus tan squared and this are going to cancel. So we shall remain with integral of d theta. Integral of d theta will give us theta plus a constant. But from here, we know that theta is given as the tan inverse of x. So that means that we are going to substitute where there is theta and say this is tan inverse of x but we have our limits from 0 to 1. Now, since you are dealing with these ones, you are going to have your calc put in radians. So put your calc in radians and then we get the answer. So I will put tan inverse of 1 minus the tan inverse of 0 when my calc is in radians. Kindly get the answer. Kindly get the answer and tell me which answer you get in the chat. Don't forget your calc must be in radians. What answer do you have? And don't forget you must show. Make sure that you show how those things come about. So you place your answer. I want to know which answer you are getting. Okay. Okay, very good. So members are getting an answer of 0.785398163. Okay, it is okay. Those who are getting pies, your calc is not in radians. Now, after integrating, this is the exact value. So it is now a matter of us getting into here and then we substitute. So, sorry, I'm going to, let me create a new slide. So I'm going to come here and create a new slide and say that now my percentage error, the percentage error is going to be my magnitude of my exact value, which is 0.785398 minus, I'm going to first check my estimated value, 0.85398, then everything times 100. So I want to first go back and get what my estimated value was. It was 0.78373. So this was the estimated value. So I'm going to write it here. The reason why we put magnitude is that your error will never be negative. So when you get that and you subtract 98, 0.785398 minus 0.78373, divide by 0.7859398 times 100. So members, what do you get? Get for me the value. Okay, very good. Members have got, our answer is 0.2. Okay, very good. So here we shall say that our error is 0.212376. And now, always avoid what we call premature approximation. Always first give your answer the way you have obtained it from the calc, to at least 4 before you go on to do it in the yes. So this is going to be 0.212%. So that is the percentage error. And don't forget to respond back to the item that may be the percentage error is this. So this is very good. Next time they may tell you, interpret the meaning. Then you have to know that when the percentage error is very small, then it means that the estimated value is very close to the exact value. Yeah. Now, those who are getting challenges with the integration for the exact value, kindly you can utilize, I think we talked about it today in the morning. You can utilize that at least, but you need to know how to differentiate and integrate, no matter how the number looks like. Yeah. And don't never forget to have your calc converted to radians. Now, this same number, the number you are seeing, could a user, I'm seeing your hand up. Can you ask?
Master,
Yes.
good afternoon, Master.
Yes, good
Like,
afternoon.
is it a must to integrate, or you can use the culture and get the exact value, since this is we are in applied and we are not in pure math, or it is a must you have to integrate?
Now, I'm going to advise that using the calc, obviously you are going to lose marks. That's number one. Use the calc just to prove your answer, whether your answer is correct or wrong. But you show. Here it is very important always to show how you are getting things. Don't just use that approach of just quoting from the calc. Show how something has come about. Because here, remember here, this is integration of topics. We are looking at, can you be able to apply knowledge from the different topics? Because you are not going to find any number that will require you to integrate that. Integrate this. Here, but here when you look at your syllabus, you looked at how to integrate tan. So here you need to apply the knowledge. That's why you call it applied. You need to apply the knowledge you have learned into this scenario, into this situation. So don't use the shortcut. Learn it as early as possible to integrate no matter how the number looks like. Okay. Now this same thing could as well be said in the scenario. That same number I've given you, that was direct, but now we can have it in the scenario form in this kind of thing. So you can read through. We could have it in this kind of format in the scenario form. But allow me now to go on such that we look at another. But okay, let people first read. Anita?
Sir,
Yes.
I would like to know why your calculators are in LOAD, yet we don't have pi in the limits.
Now, one thing you need to know that whenever we write tan, cos, and sine, or any trigonometric function, always the angle you have here is in radians. Is that okay, Anita? That angle you write there is always in radians. And if it is in degrees, they will always specify that x degrees. Hope that is okay.
Yeah, I've got it.
Yeah. And now, in fact, if you have in pi already, there is no need for you to convert your calc in radians. If it is already in pi, there is no need for you to convert your calc to radians. Okay. Let's go to the second one. Item number 2. I'm going to first ask you to read, and then we start. Read. Is it Powell? Yes?
Yes, good afternoon, sir.
Yes, good afternoon.
My question is a bit controversial. I was asking if we can access the recordings of the morning lesson.
Yes, they are already on the group. Just check on the holistic e-learning. We usually post them there.
Oh, okay.
Okay. Yes, Melissa?
Master was asking now for these scenarios, how do you know that they want you to use the trapezium rule?
Yeah. Now, one, you need to be very careful with the wording, how they put the wording. When they tell you to estimate, like when you look at this item, they tell you that estimate the total effective response. You know that estimation, they are asking you to use the estimation approach. And one way to estimate, as long as you know the difference when to integrate and when to differentiate. But like you need to understand that trapezium rule is all about what it does is to find an accumulation of something. Then the method for estimating is the trapezium rule. Other methods, you have not looked at them yet. The longecutors, you have not looked at those ones. So you cannot be, that is the best that you can get. Is that fine? Melissa, I don't know whether you have got that. Yes. So you need to understand. That's why when we are starting, I wanted you to understand, yes, the estimation methods. Eh, Okay, are we going to start? Let me know through the chat that now people have looked through. Are we going to start? Let me know, and then we start. Okay. Okay, I think we are good to start. We are good to start. Okay, now when you look at this item, it is a model. Someone has come up with a model, and they have told us that research team is monitoring the growth of a newly discovered biological substance in the laboratory. Science have observed the substance accumulates rapidly during the early stages of the reaction, and the rate of accumulation is given by this. From the experiment observations, the rate of accumulation was modeled by this, whereby X represents the time in hours and R represents the rate of accumulation of the substance. Now, during the first hour of the experiment, measurements were recorded at equally spaced time intervals because of that this and this. Yeah. So now that is what we are going to be looking at. Now, I'm going to stop sharing for a minute. You're going to allow me to stop sharing for a minute, but I'm going to share. It should not worry you. Yeah, I'm going to share. Now on my screen, I want to share. Hope you can see. Okay, sorry. I want to show you the graph, because like I've said that many times, all these are graphs. So when I come here on my screen, you are going to look at that curve. The curve is x squared e x. Yeah, so that is how the curve looks like. Now, when you look at this curve, they have told you that during the first hour. Now, this is where reasoning is very important. You ask yourself, can we have negatives? That no. That means that when they are timing, they are going to start their clock from here. And where are they ending? Where you have 1. At this point here, this is where we are going to end. Let me make it big such that people can be able to visualize it better. Allow me to make it big. Oh, but now it is becoming very big. Okay, somewhere there. Now, it is up to you to know that if this is from 0 and this is 1. Now, if they have not given you, they have given you the like the timing that they are monitoring it from 0 to 1, and like they have told you it is increasing. And surely when you look at it, this curve is an increasing curve. Things are increasing rapidly. And when you look at it, it is going onwards. Now, what does it mean? Now you need to sit down and ask yourself, what am I going to use as my sub-intervals? The first scenario is that just imagine they have just given you 0 to 1. You may ask yourself, what can I use? It is okay for you to ask, as long as what you are using gives you equal spaces. But the beauty from what we have here, they have already given us what to use. They have already given us what to use. So we are going to use what has been given. But since good enough, I've showed you how it looks like graphically. That's why now here, when you are reading, your knowledge of graphical construction, that thing of curve sketching, you need to be very good. Now, when you look at our laboratory results, kindly look at this picture here. They have told that the measurements were recorded at equally spaced time intervals, and they are here. Now, they have given us from 0 up to 1. Now, if I may ask members in the chat, how many ordinates do we have from those values that were given? Put in the chat quickly. I want to see. Thank you, Emerson. Emerson has said there were 6 ordinates. Very good, very good, very good. Members, number two. If I may ask, what is the sub-interval value? The area, like that's I think what I want. What is your H? Just looking at the values. Or how are you going to get your H? Very good. Jim has said 0.2. Now you need to know here 0.2. Now, are you noticing that here it's just about understanding that now here I wouldn't expect members to go and say B minus A out of N. No, because the values they have already told you that they are at equally spaced, meaning that and I told you that in order for you to get H, get the difference between the two ordinates. So that means you are going to just say 0.2 minus 0, which is 0.2. Or someone could say 1.0 minus 0.8, which is 0.2. This is where now understanding is very important. You don't operate on the other crumbed thing that always I have to divide, I have to what? To divide. So that what does it mean? That sometimes you may find that even they have drawn for you the table. Are you getting it? You may find that they have drawn for you the table and they are requiring you to understand. Now, since they have already drawn for us the table, we are going to use it the way it is, the table. So we are not going to go on and put our things. So now here, I'm going to have our table here, whereby we have our X, and from the table, according to the table, we had 0 to 1. So it was starting from 0, 0.2, 0.4, 0.6, 0.8, and 1.0. Now, when you look at R, here up, when you look at it very well, they put for you the rate R unit per hour. So that is what we are going to have here. So that is going to be our R. You put it the way it has been given. Don't change things the way you are. So that's why understanding now is very key. So I'm going to come here. 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 Now our R was given as x squared e power x. I think something like that. Yeah. So now, members, can we go on and substitute in our values, substitute in your 0, substitute in your 0.2, and all the rest of the values. Yes, substitute in the values. Yes, Deborah?
Excuse me, teacher.
Deborah? Oh, I'm not getting you. I'm not getting you. Can someone raise up the hand? Anyone who has finished the table, raise up the hand and you give us the values you have in the table. In case you have finished your table, just raise up the hand and you give us the values you have in the table. Deborah, your voice is low. I want someone who has finished to raise up and you just tell us the value you have. Deborah?
Yes, please.
Yes, your voice is low. I can't hear. Alex?
Okay.
So for 0, the answer is 0.
Okay.
0.2, we have 0.048856. 0.048856.
Okay. Okay.
0.4, we have 0.238691.
Okay.
991, oh yeah, sorry, 92, sorry.
Okay.
0.6, we have 0.65596.
Okay.
Then 0.8, we have 1.42435.
Come again. 1 point.
1.42435.
Okay.
Then for 1, we have 2.71828.
Okay. Thank you. Thank you. Yes. Now that is how our table is going to look like. Now, since they have told us to estimate, so now we are going to come and even better always use the value. They have told us estimate the total amount of substance accumulated during the first hour. So I'm going to come here and I say now total amount accumulated. Total amount accumulated will be approximately equal to, I write my formula, a half of h into y naught plus yn. Now, in case someone wants, you could even transform this formula. I don't know whether I can now transform it, but you can transform it and write it in terms of r. That is very okay. Plus 2 into y1 plus y2 plus y3 plus y4. Yeah, something like that. Then you put in now your values, a half times 0.2 into your value of y naught, which is 0, plus 2.718282 plus 2 into 0.04885. Okay, you add up all those values. Eh, eh. So I'm going to wait for someone to finish and then you tell us your final answer. As I pick a hand from Deborah. Deborah, I failed to get you. Talemwa. Okay, I think I failed to get Talemwa. Then Grace.
Excuse me, sir. Please pardon on how they put the function into the calc.
Oh, okay. Which calc are you using?
Scientific.
No, like they have types. Is it this new version or the old version?
The old one. Old
The
version.
old one. Now, the old one, you are going to, you are listening, eh? You are going to place alpha.
Yes.
Okay, but now, okay, you have placed alpha.
Yes, sir.
Place on your calc, there is somewhere where you have a bracket where there is x. Place that x.
Yes.
Then look out for squared on your calc. You have placed?
Yes.
Place shift and place lean.
Yeah.
As the e come.
Yes.
Now go to alpha and place x. Placed?
Okay.
Yeah? Then
Yes.
after you place solve, go where there is calc. There is a word solve.
Yes.
Seen?
Yeah.
And now you just place in 0, you place equal sign.
Yeah.
What have you obtained?
0.
You place back solve.
Yeah.
And then you place in those values. Then you place equals.
Okay.
It has come?
Yes.
Okay. Okay. Okay, members, I'm looking through the chat. I want the final answer. The final answer. 0.75, 0.74. Okay, 0.74540. Okay, I think that's what members are getting. So I will take it as the gospel truth, 0.745412. And remember, these are square. But now you can go back and look at, they might have given you units. In case they give you units, you use the units. So when you look here, you notice that, what do you have? Which units are we going to use? Do we have units? Okay, they did not specify the kind of units. So those are units. You say square units. And I don't expect people to tell us that those are hours, because the answer we are getting, that is the substance that accumulates in the body. So they did not give us the specific units. So you just say square units. But you conclude well that the estimated amount of substance accumulated in the first hour is that. Now, I don't know, I'm seeing hands. Kenneth, Juliet. Okay, I think I'll fail to get you. So members, I think kindly let me know. Are, are we good to continue? Kindly let me know in the chat. Are we good to continue?
Excuse me.
Continue. Okay, yes. So we are going to continue. Juliet?
Yes.
Yes, please. Is it a question?
For me, I'm getting 0.745399
0.7 what?
4
Hmm.
5996.
Okay, I think the answer is around that area.
Yes, but have you said that you gave us for adding everything?
Yes?
Have you said that you gave us your first add the ones in
That's
the
what? You are saying?
I've used the other first method you gave us for first adding everything.
Oh, yes, your answer should be the same.
Yes.
It is okay, Juliet. That is okay.
Okay.
Yeah. Yeah. Yes, Martina?
So I just wanted to clarify. We
Hmm.
only put our calc in radians when we are working with trigonometric functions and radian, like when they give you pi as the limit.
Now, when you have pi and you are going to place on your calc the pi, yes, you convert your calc in radians.
Okay.
Anything with the trigonometry, place it in radians. As long as it is sine, cos, tan, the moment you meet such, your calc should be in radians. However, don't forget to take it back. Because when you forget to take it back, you may end up getting wrong things depending on what you are working on. Hope we are okay. Okay, I think we can now continue. Now, we go to the second one. Now, when you look at the second thing, they asked you that later in the main laboratory, they wanted to determine the exact total accumulation during the first hour. Now, what are they doing? They are indirectly asking you to obtain the exact value. Now, let me ask in the chat, which approach, when you look at the kind of integral we have here, which kind? Remember now we are going to move the first hour, we shall move from 0 to 1, but I may not put the limits for now. With respect to the x. Members in the chat, which approach do you think we are going to use to come up with the exact value here? Very good. Integration by parts. By parts. Perfect. Perfect. That's why now you see that these things, you need to know them. Yeah, integration by parts. So, and that's what we covered at the first, I think on Monday. And we say that integration by parts, the moment you notice that you have two functions that you are multiplying, the product of two, then that's where the idea must come in. So here, remember, we said by integration by parts, we shall have our uv minus the integral of v du dx, then times the dx. Members, you tell me what is going to be our u and what is our dv. Yes, Jimmy has mentioned, Martina has already said, Greenway, yes. Our u is x squared. Yes, Melissa.
I wanted to try that part.
It is very okay, Melissa. Start.
Okay. Our u is equal to x squared. And then when we differentiate it, du dx, we get 2x.
Okay.
Then we need the v, so we are going to take our dv dx as ex exponential x. Then we write dv is equal to ex dx. We integrate both sides, and then our v is equal to ex, because when you differentiate an exponential, you get that exponential.
Perfect.
Then you substitute back in the other formula. Our u is x squared, then v is ex minus the integral of ex, then our du dx is 2x. So according to what we have, we need to integrate again. So we are integrating 2x ex. So in this case, our u is 2x and our ex is equal to the v. Yeah. V is equal to ex after integrating. So our formula becomes, then we substitute back to the other formula, we get 2x.
Oh, okay.
Sorry.
Okay.
2x.
Oh, we are substituting here, right?
No, I'm still this side, the
Okay.
integral of 2. Yes.
Okay.
So 2x 2x ex minus the integral of ex times 2. So since 2 is a constant, when we write 2x ex minus that 2. When we integrate ex, we get ex. So we substitute back to the other main equation 1. Yeah. So we get, that one. We get x squared ex minus 2x ex plus 2ex plus c. And then the question was saying that for the first hour, so we have to first get initially. Initially, the time was 0 equal to 0. And then that means the total substance is also equal to 0.
Are you sure?
I don't know.
First substitute and confirm.
Oh, no. Okay, we first substitute. X is that 0 squared E0 minus 2 0E0 plus 2 E, yeah, plus. Now I'm asking if we are saying that the total substance is not equal to 0, that means we have two unknowns. But in our
No,
table we
it
go
is
to the
okay. It is okay.
yeah.
The total substance is 0. That is true.
Yeah.
Uh-huh.
Now calculate. Someone help me there with the calculator.
What is e to power 0?
One.
1. So this is 0, this is 0, this is 2 plus c.
C is equal to -2.
Okay.
So we get total substance after 1 hour. X is equal to x is equal to 1.
After 1 hour?
Yeah, after 1 hour. X is equal to, so we get 1 squared E1.
Let members do the calculations and we see as you do. Do you have a calc, Melissa?
I don't have one here.
Okay. Let's see what members get. Okay. Members are getting E. Where are members getting 0? Members, why are you getting 0.7? Something is not okay. Yeah, I'm not getting that. Hey, remember, I'm not saying where 0.7 is coming because here I have E minus 2E plus 2E minus 2. Minus 2E plus 2E is 0. So I get E minus 2. Oh, okay. So E minus 2, E1 minus 2, which gives... Oh. Yes, I've seen. I've seen where the problem is. Sorry. You are... But still, members, what do you get? You get that E1 minus 2. Thank you, Samuel. Now I'm getting the same answer. Even if it is the final answer, me, I have this. Where are you getting? Yes, place your calc very well. There is a problem. Hey, now, hope members you changed back. 0.7. Yes. Now that is okay. That is okay. That is okay. That is very okay. Now I think we are agreeing with the answer. Thank you, Melissa. Now, members, let me hope now you have seen that you having knowledge of just one topic cannot save you. Yes. And I pray that, hope you know what. Yes, Itel. Okay. I failed to get Itel. So that is how we integrate that. So now that we have obtained that, I think that it was the exact value. And then the next part wanted us to obtain the percentage error. So can we calculate the percentage error on our own? Calculate the percentage error on your own, and then you share with us what you get. Rena? Rena? Okay, I'll fail to get Rena. I see something like that.
Excuse me, sir. Like, what final answer did you get?
0.7 something.
Okay.
What do you have?
I had 0.718.
Yes, that is very true.
Okay.
Okay, now we are getting the percentage error. Yes, I tell.
Excuse me, teacher.
Yes.
We have not understood how they integrated by parts. Maybe you can take us through again.
Oh, did you attend the lesson on Monday?
I missed that lesson on Monday.
Okay, now I'm going to request, because on Monday we had 2 hours of looking at how we integrate by parts. So you need to get the foundation, but whenever we are dealing with integration by parts, you must look at which one is easier to differentiate and which one is easier to integrate. But whenever you meet an exponential function, maybe with an algebraic function, if you have practice, you will notice that the algebraic function can diminish over time. But of which now, an exponential function is one of the functions in math that is very annoying. One of the reason is that I think even some of you have those friends of yours. Someone who doesn't add anything on you, there is nothing he adds on you. He's just there as if he's adding, as if he's not adding anything. So that's how an exponential function looks like. You are going to integrate it, you'll get the same answer. You are going to differentiate it, you get the same what? Same answer. So that one is, for it does not diminish. It goes, yeah. Yes, Martina, what are you getting?
Teacher, I'm getting 3.775%.
3.775, eh?
Yes.
Okay. I think that's what also others are getting. Yeah. Okay, thank you. Okay, 3.775%. Okay. All right. Yeah. Why don't we stop here? But allow me, why don't I give you, this as your homework? Just take a screenshot. In case they ask how the errors must be reduced, then that's when you say that, depending, you need now to reason that, okay, let me go back. Hope members have taken the screenshot. Yes, now members, just assume they have told us that they have asked us how we can reduce the errors in this number. What would be your response from the scenario? Basing on the scenario. Yes, Sema? Okay, I'm failing to get Sema. Yes, Martina?
To reduce the errors, we can increase the number of ordinates or the number of subintervals.
Now don't go out. Now I want you to relate it to the scenario. When you look at the scenario, what represents the ordinate? So you need to be in that direction of what the scenario has.
Okay. In my opinion, what's representing the ordinates and the subintervals is the time in hours. So I think they can increase the time for the experiment. Yes. Time taken
Now,
to make the experiment.
come again.
I think they can increase the time for the experiment.
Now, don't go away. Remember, they have told us that they want to take it for the first 1 hour, not so?
Yes.
Yes. So if it is for the first one, because that's what they want. Now, if you increase the time, the way you are saying, what is going to happen?
I feel like if I increase the time, the rate of accumulation is also going to increase.
Mhm. There is something. But I know the other first one is okay. The other first one of audience what? But now we need to relate it to the scenario. There is some way you need to look at what has been given and then you let me first say, you keep thinking. The wording there is something that is not yet coming out. But leave your microphone open as you think.
Master, I think we should record for short periods of time.
Short periods of
Time, like for if they had been recording for 0.2, they should record for 0.1, 0.1, 0.1 as they accumulate for 1 hour.
Okay. Thank you, Jimmy. Let me hear from Alex. As Martina also you think about the answer, They have given us.
Uh,
Yes, Alex?
yeah, I think I also agree with Jimmy.
Mm.
Tracer errors, they need to increase the time intervals taken between that 1 hour. They increase the number of time intervals, yeah. Like let's say from 0 to 0.1, 0.2, all that. Yeah.
Okay. Thank you. Sema, the same?
It's the same, increasing the time intervals.
Okay.
But also,
Martina, what do
I
you have
was
to
just
say now? Come
Okay,
again?
teacher, what I have to say, I feel like what from Jimmy's response and the other post response, I've now understood. Like 0 in this case is our lower limit and 1 is the upper limit. So by increasing the time intervals, like they said, we are sort of increasing the number of ordinates. So now instead of having, let's say, from 0 to 0.2, we can have 0, 0.1, 0.2, 0.3, like that. So by doing that, we'll be increasing the number of ordinates and therefore reducing increasing the accuracy. Yeah.
Okay. Yeah. So now here, members, as we go on, you need to know how to put that wording when you meet these scenarios. Joan here, when I check, Joan has said, reduce the time between intervals when you are recording the measurements. So that explanation members are giving, so you need to get a way you correlate. But I know you have the ideas, like we have said, that for you to improve the accuracy, that if at first they were recording after 0.2, 0.4, 0.6, so you keep, like you reduce you make that time smaller, like maybe 0.1, 0.0, like something like that. Yeah, but I think Joanne has framed it well. Jimmy, yeah. Now I think that is the idea you need to have. So that means that if you have not seen here ordinance, don't bring in the knowledge of ordinance. You have not seen sub-intervals, don't bring in what? Sub-intervals. So you must respond in the direction where the scenario is leading you to. Yes, Juma.
So, good evening.
Yes, good evening.
Mister, I wanted to take you a little bit back about the other item 1. It had it had the function 1 out of 1 plus x squared. Then I'm asking, is it possible to first turn it? Then I first bring this denominator up, then I don't use the other method of the turn substitution. I use the one for integration by parts.
Here?
Yeah. No,
what
not
is going
this
to be?
one.
Yeah.
The first one, not this one.
Okay. Yeah. I'm writing here what you are saying.
Yeah, that's the fact.
Now you are going to ask yourself what is going to be your U.
My U. Then I thought that when I bring this up, I can use 1 as my U.
You 1 as your U.
No, I can use 1 as my dv. Then I can use this 1 plus x squared as my U.
1 plus x squared power negative 1 as your U.
Yes. Yes.
Go on and differentiate for us this. What do you get?
When I differentiate, I'm getting negative.
Okay. For me, let me write for you. You are going to get something like that.
Yes.
Okay. Now, you are not saying, meaning that you are going to write your U at first as this. Are you seeing? Then times your V, which is going to be X, minus. Now, your V is X times negative 2X out of 1 plus X squared, then power of 2.
Power of 2.
Now, instead, you are making your fraction much bigger.
Okay.
So you are complicating it further. So the choice of which integration approach to use is very important.
Okay. Thank you, sir.
Okay.
Sir,
The answer, yes?
away from this, I'm just asking about. I saw a message saying that you already covered area under a curve. Is there any chance of finding it on YouTube? Also, the concept of volume.
No,
Volume of
someone
a
was
curve.
talking about integration. I think it was the first lesson on integration.
So that you covered it.
We covered, look, like I was showing them the applications, but in case in future time allows, maybe we shall cover it.
Okay, sir.
Okay, members, I think Grace, unless it is a burning question, and Galax, is it a burning question?
Good afternoon, sir.
Yes, good afternoon.
Sir, I have a question on this. When I'm getting y1, y2, if I leave my answer as a fraction, is it okay?
Yes, it is very okay.
So even though I don't use decimals.
Even if you don't use decimals. However, the only problem will come in when you fill in. Let me say you have obtained 1 out of 1 plus a half squared.
Yes.
Sometimes children find problems with dealing with the decimals. And now even placing that on the calc, it will waste a lot of time. Yeah.
Okay, thank you, sir.
Okay. Yeah, I think we are going to Bakita. Yes. Yeah.
Could you please pardon on how to get the percentage error? Because at the beginning of the lesson,
I'm just inquiring how to do.
The percentage error, we said you get the magnitude of the exact value minus the estimated value, the value you have got from the trapezium rule, divide by the exact value, then times 100.
Thank you, sir.
Okay. Bakita, I think you wanted something. Otherwise, members, I expect you to be doing this question as members still talk. Be doing this item.
Excuse me.
Yes.
Here I talked of a terminating number. We should write the h when it is a fraction. When it is a fraction, and you said you talked of a terminating number, but I did not understand what was a terminating number.
A
Could you please?
terminating decimal is that one where it can end somewhere. Let me say you have 1 out of 3 and 1 out of 2. 1 out of 3 is 0.3333333. It is recurring. 1 out of 2 is 0.5. This is terminating.
Oh.
Yeah.
Oh, thank
Yeah.
you.
So using subintervals that are recurring is deadly. You accumulate a lot of errors. Gaba, Adrian, and then her. Okay. I'll fail to get them. So members, let's meet tomorrow morning, same time. Tomorrow morning at 5 a.m. sharp. We always start on time. 5 a.m. is 5 a.m. And then tomorrow we shall look at, we are going to look at trapezium rule, but we are going now to look at those cases where we have trigonometric functions. That's what we shall look at. And once we finish it, tomorrow we shall finish this topic about trapezium rule. And that now I know you will be ready for the thing. We use the same link. This is the same link. This is the same room. Even if you don't see the link in the group, this is the same that we always use. As if there are some people who are not on the group. Let me pick the link.
Excuse me, teacher.
Yes?
Good afternoon, teacher.
Yes, good afternoon.
So, teacher, okay, the problem is, okay, we are requesting for the link, like where you post the YouTube, like the lessons that have already happened.
Oh, now.
Yes.
Okay, let me first post this link. Those who are not on the WhatsApp, that is the link.
Thank you, teacher.
Okay, now it is holistic e-learning, the YouTube. It's called holistic e-learning. That's where we place them. Here. For you, just go here and then you'll find them on this link. That's where they are. Yeah, but I've placed them in the playlist there. For you, just check on the playlist. Then you'll check that this is trigonometry. This is for senior 5. Now your integration is going to be here. But now I'm going to create another and maybe for trapezium rule alone. So that's where you'll find. Then those who missed vectors is here. Differentiation 2 is here. Those who are asking about curve sketching, something like that. It is there. Curve sketching. Yeah, you'll check out. Yeah. Okay. So, I don't know what you are saying, and Juliet, but the rest, please, we can drop off. Ali, yes?
I think
You are saying